about now, we want to start. And the first class we'll be having is entitled Introduction to Gases. We have as a facilitator for this class, Mr. Rasaq Oyenola. Rasaq, you have our undivided attention.
Thank you very much, Mr. Olakole. Good afternoon, distinguished ladies and gentlemen. My name is Rasaq Oyenola, and as the ES, the Executive Secretary of NLPGA, has rightly mentioned, I'll be doing justice to the topic called Introduction to Gases. You would agree with me that for us to know how a certain thing behaves, the key foundation is knowing exactly the concept on which these things are formed. Now, we would try as much as possible during the course of this presentation, this masterclass, to go as elementary as possible, void of the major technicalities that some of us are familiar with. And we'll try to use day-to-day examples, images, experiences to depict what we essentially mean by these basic concepts. Here is my outline for the topic for today, Introduction to Gases. The first concept that we need to understand is understanding that gases, the correlation between pressure and gases itself. The second is temperature, third, volume, and the fourth is composition. And lastly, I'll be knitting it up together by telling us the relationship between pressure, temperature, volume, and composition, upon which this basic concept, we would be able to relate what brought us here, and that is the product, liquefied petroleum gas. Having understood what gases behavior looks like, we can invariably understand how LPG also behaves. All right. I'll start on with the first outline in my prelude, and that's pressure. What exactly is pressure? Now, let's take a look at the image to my right. We have a balloon and a fist. Now, imagine you held a balloon and you jab it with your fist with a little effort. I would ask what would happen? What would consequently happen is that the balloon will maintain its position as it were, whilst our hand or our fist with a little effort would literally bounce back from the balloon. Now, take a look at the second image. You realize that between our fist and the balloon, we have somewhat like a needle or a pin, if you may choose to call it. So what would happen with the same amount of little effort in image 1, and we replicate that in image 2? We realize that the balloon it would give way, it would pop. The science behind this is just simple, is that the force that has been applied in image 1 is the same, is equal as the force in image 2. But the only difference is that the area on which this force is acting upon is smaller in image 2 relative to image 1. And that is the reason why the pressure in image 2 is greater than that of image 1. All right? I would use another example here in the second slide. Now, before I move on to that example, the basic knowledge of pressure that we know over time is force per square area, right? So that technically means mathematically, we're saying force over area. Area, we all know what area is. So for me to go as elementary as I had mentioned earlier, I would introduce weight in place of force. I mean, some of us go to the hospital and have our weight measured. We stand on the scale, and the gravitational pull of our body upon the scale is what gives us. Essentially, that is what also force means. All right. So for elementary purpose, we say weight in this case. Now take a look at the image here, a rectangular brick. All right. We know that with the equation that is here, we have area as 20 square meter. And let's assume this brick is 100 kilogram. What we're essentially saying that the weight of this brick is 100 kilogram, acting upon an area of 20 square meter. What does the pressure entail? It shows that is 5 kilogram per meter square mathematically. But the time we change the orientation of this brick and make it stand vertically, we realize that it's the same brick with the same weight, but now it's acting upon a smaller area. And consequently, what this shows is that the pressure would be different from image 1. And we can see that significantly the pressure had increased because the area it's acting upon is literally, or compared to the first one, is smaller. All right. Now, what we have here is just buttressing and reiterating what I have mentioned in the first two slides. So I wouldn't dwell upon this. It's just essentially mentioning that the pressure has changed or is different from image 1 and image 2. Essentially the same thing that we have talked in the first slide and the second slide. So we can literally choose our poison and see that the force is quite different. Now, moving on. Now we want to discuss other aspects of how pressure affects us. Now, as a child, or if we have to be reminiscent of how we spent our childhood days, some of us here have carried out this kind of stunts, having water in a cup and you tilt it the other way around with a piece of paper or say plywood, and you realize that the water maintains in the cup. It is no miracle, it's just science that the atmospheric pressure is acting upwards upon the weight, which makes it equal and avoid the water from spilling. Now, what is this atmospheric pressure that we have mentioned? Let's just take a look at a couple of fun facts about atmospheric pressure, all right? Atmospheric pressure is the force that is exerted on a unit area of the Earth's surface. And this is because I had mentioned that how does pressure affect us? So atmospheric pressure is all around us. And that's why you can have an item placed somewhere and you meet it there in 100 years, unless an external force has come in contact with it. So atmospheric pressure on an object is in all directions at any particular point. And that's why we have these arrows showing that atmospheric pressure is at every angle on the Earth crushed. All right, moving on as well. Consequently, I have mentioned what pressure is, but here is just for us to relate aptly with the product we're talking about. So we're talking about LPG, which is a gas, is a fluid. All right, fluid entails liquid or gases. And now, what I'm essentially trying to buttress here is that pressure would move from a higher region to a lower region. A classic example is our cocktail or a cup that has a Coke and ice in it, and you have your straw dipped into it. What do we often observe is that the fluid will not get into the straw unless you have tried to suck the straw. And by doing so, you have created a vacuum in the straw, and that's why the fluid moves from the cup into your mouth. So technically, what we are saying is that it moves from a higher region to that of a lower region. So when you have your LPG tank and you have a pressure within a tank with a gas or a pipeline orientation, you discover that the pressure at a higher level will move to that of a lower level. And here are day-to-day application of pressure. Our SPIG, when we're in the hospital, check our blood pressure. Aerosols, pressure pots, this is an interesting one. And along the course of my presentation, we'll talk more about this pressure pot because it is essential to how I want to make us understand elementarily what pressure means. And lastly, we have the pump we use in pumping our tires. These are examples. And keep in mind that pressure can be measured in various methods and various ways. The first is kilopascal in bar, in pounds per square inches, and in kilogram per square meter. Now take a look at having me put in a bracket. Apologies, please. You see bracket A and bracket G. What that essentially means is that A means absolute and G means gauge. What this means is that pressure is measured in absolute terms and in gauge terms. And that will be too technical for the purpose of this class. But what we are saying in absolute terms, it means it's measured in zero datum. That is in vacuum, all right, like in space. And gauge is what we have here on sea level and of course, under sea level. Now let's move on to, hello, can you hear me? Okay, apologies for the drop there. We had some technical issues. Temperature now, we have moved on from pressure, now we're on temperature. And temperature essentially means the average kinetic energy of the particles in the system. This is otherwise known as heat energy. Need I mention here that a lot of us misconstrue what heat is compared to temperature. Heat isn't exactly temperature, but temperature is the measurement of the heat energy exactly. So when you have your water boil and displacement of these particles when the water boils, that measure of the degree of that displacement, the kinetic energy, is what temperature is. Invariably, we are saying that the higher the temperature, it means that the higher the heat energy and the faster the moving particles. Now, for the purpose of this class, we'll mention the primary standards to which temperatures are measured, and that's in Celsius and in Fahrenheit. Now, we're moving on, and here we're going to discuss thermal equilibrium. Temperature always moves, temperature moves from a region from hot to cold. So a very typical example we have here is like a cup of coffee. For some of us that have the coffee brown, you realize that when you introduce your cold milk or your tin milk, whether cold or warm, the temperature of the coffee begins to drop. And that's because the hot fluid has mixed with the cold one. And another way we can look at it is if you have a glass cup or your cup of coffee still, when you have the tea in it and it's hot, you realize that at a certain point in time, when you grab this cup, your temperature of your palm begins to measure up with the temperature of the cup. And at some point, it gets to an equal temperature between your palm and the cup, and that is known as thermal equilibrium. In temperature, it is essential we discuss states of matter, all right? Solid is such that a matter is closely packed. The particles are closely merged together. But for liquid, we have it loosely or averagely loosely packed, while in gas, it is more loose than that of water. All right, so solid is compact together, and we are going to try to explain further using, say, the phases of water. We have the solid ice packs, we have the liquid, and we have the gas. And for every case, you can recover and you can dissipate, just like how you can have solid ice turn to water, liquid, sorry, and you can have liquid turn to gas. And vis-a-vis, you can have gas recoverable back to liquid and liquid freeze onto solid. And these are the terminologies for the states of matter. Upon here, we'll be discussing how we can apply temperature in our day-to-day lives and how we have seen it, so we can relate with temperature as it concerns solid expansion, in this case, a railway track, and that's why we have spaces within our railway. This is to depict, or this is to give room for expansion of these metals. Also in our gas pipeline orientation, when it's being constructed, spaces are given allowable for the metals to expand. For liquids, what we can relate with is our typical thermometers, graduated and of course calibrated. You have the liquid within this containment, and it's sort of designed that when the temperature heats up, the liquid expands, and then we have our readings for our thermometer. An interesting one is the gas expansion. This is a methodology behind that. When you have hot air, is lighter than when you have cold air. So essentially, the air is burned within the balloon, and it is cooler and is lighter than the surrounding cooler air around it, and that will make it float upwards. So that is what we know as gas expansion. And this is critical for our products in LPG for us to understand how they behave. Okay, now we've gotten to the third concept. We have treated pressure, we have treated temperature. Now we are on to volume. And it's key to understand that volume is a three-dimensional space. What this essentially means is that a fluid would take the position or would take the orientation of a physical containment. However, we have a drum, a cylinder, a sphere, or a square. The volume would take the position of how the containment properties are like. All right, so volumes are also enclosed, they're also in enclosed surfaces. So essentially, if we're trying to say we are discussing volume, we should also talk about how it's being measured. And the most common one is by cubic meter, which we are most familiar with, cubic feet and cubic centimeters. Other methods are liters. 1,000 cubic centimeters. This is a similitude to our car engines. They are measured in cc's. For some of us that are car freaks, you see that the engine of the vehicle is measured in cc. In gallons, either in US gallons or UK gallons. These have different variables in achieving the calculation. All right, and lastly, barrels. Of course, in barrels, these are the ones that are synonymous to the crude oil industry. That's how we have, they say, Nigerian exports XYZ number of barrels, because volume can also be measured in barrels. Like I have mentioned for pressure and temperature, we'll talk about how we can, our everyday application of volume so that we may understand. Now, let's just take our minds and picture our dashboards for our cars. We know oftentimes we see our field either empty, full, quarter full, or what have you. This is the idea behind this is that the containment of this field is measured by the height of the cylinder or the housing of the field. So by the height or the depth or the length, you can describe how a volume is distributed in a vessel or in a containment. Okay. Now, this is the fourth basic concept in discussing or understanding how gases behave. I mean, keep in mind that the topic is introduction of gases, all right? So we are essentially saying that composition is the degree to which elements are distributed in a mixture. Like I've used classic examples for the others, I will use same for composition. And our ORT is a typical example where you have sugar dissolved in water. You discover that the properties of water would change. The salt or the sugar would have altered some of the characteristics or chemical composition of the water. This is what we mean by composition, having 1, 2, 3 elements in a certain composition, all right? Now, I am trying to illustrate better using air, which is like layman's term, like gas. It would appear more like we're discussing gas, all right? And here we have nitrogen at 78%, of course, composition of air, and oxygen at 21%, and the other gases. What happens when you alter one of these natural phases of how God has distributed the air? For example, we increase oxygen. We discover that, apologies please, we discover that oxygen enrichment, at the classic safety understanding is that it would make the environment very volatile, means fire can ignite quickly. Some of my colleagues will discuss some of these things during the course of their presentation as well. So when we deplete oxygen, what then happens? We realize that that place is uninhabitable. I'm essentially relating this to composition for us to know that properties of a composition would alter by the degree to which we change elements. So here we have an extraction of NIS 555. This is just a standard. NIS means Nigerian Industrial Standard, all right? And we have copped one part out, and this shows a vapor pressure at 37.8 degrees. Keep in mind, here I'm mentioning bar gauge. And it says that domestic LPG will become 6 bar, while commercial propane will become 12 bar, and commercial butane would become 4 bar. Now, before I started off, I didn't mention the constituents of LPG. And the domestic LPG that you have in your kitchen homes is made up of propane, butane, and other trace elements in it. And propane is distributed about 30%, while butane is 70%. So essentially, you can understand and relate with what I mean by composition. And here you have commercial propane at 95%, whilst butane is 2%, and others, which is trace, about 3%. Commercial butane is 95% in the third image here, in the pie chart, sorry. And propane is 2%, while you have the other trace elements in there as 3%. So you can see that this is how they are distributed. So in this composition, you would agree with me that if you alter the concentration of domestic LPG, for example, the vapor pressure would also change considerably, okay? Now, here is where I begin to knit up the 4 basic concepts of pressure, volume, temperature, and composition. And like I mentioned that I said I was going to get to, here is our pressure cooker. It's an interesting tool used in the kitchen. And why I'm saying this is that it would help us relate better with what we mean by pressure we're saying, and temperature. And you would agree also that for our ladies or our chefs in the house that make use of pressure cooker, they achieve cooking faster. Why is that so? The orientation for this is that there's higher pressure using the pressure cooker, hence you would achieve a higher temperature. Essentially, this is what this slide is trying to tell us. And then we'll be talking more on this volume, pressure, temperature correlation with a thermal expansion. Now, take this, my first image, to be an LPG tank on a normal day, and we have a temperature at 20 degrees. Our pressure is at 10 bar, and then the mass is at 10 empty, whilst the volume is at 20 cubic meter. You realize that the cold day, the temperature obviously would have dropped to, say, assumption, 0 degrees centigrade. What then happens is that we see that our pressure considerably drops as the temperature drops, or You can use it as the pressure drops, the temperature drops, and consequently the volume also drops. And on a hot day where we have the temperature rising to 40 degrees, you would see that the volume would increase so as the pressure would increase. This will enable us understand what I am trying to say better. The TG replicates temperature gauge, PG pressure gauge, LG level gauge. And you can see on a cold day where we have the level of our LPG, for instance. And the second slide showing a hot day when the temperature has risen significantly and the pressure consequently has risen as well. And you will realize that the level gauge compared to the first has gone up. So it means the volume has increased. Now, all of what I have been saying from slide 1 until this point is that you cannot know your product. And our product in this case is liquefied petroleum gas. You can't have a hang on it unless you understand exactly how gases behave. All right? Knowing pressure, volume, temperature, and composition will give you a lot of latitude to understand exactly the concept, how this LPG, this 4 basic concepts interact. It gives you a broader knowledge. And then lastly, the relationship between these basic concepts is what will guide our every safety action with regards to the use of LPG. Thank you for making me your tutor for today. I hope that you have taken 1 or 2 things home from this presentation. I'm glad to have been one of the panelists today. Thank you very much.